Hi everyone, welcome to the video solution guide to problems number 4 and 5 from the third problem set. In this problem we're asked to find the horizontal velocity, or how fast the dog would need to run in order to clear 8 meters if it takes off purely horizontally. And this is a dog taking off or jumping off of a dock, and it's jumping into a pool of water, and the water is 1 meter below the surface of the dock. So the first thing that we want to do is we want to set up a diagram of the problem. So if this is our dock, and we have a splash here in the water where the dog has landed, and we know that this dog has traveled 8 meters in the horizontal direction, and it's traveled 1 meter in the vertical direction. The last thing we want to do is set up our coordinate system, and we'll set this up right here at the corner of the dock, so that to the right is positive x and upward is positive y. Now what we can do is we can write out all of our known quantities. So we know the horizontal displacement in the x direction is equal to 8 meters. We know the vertical displacement in the y direction, obviously it's in the y direction, and it's equal to minus 1 meters, and that's because it's traveling down from this point. The origin at the dock is traveling negative 1 meters down to the water. We know that there is acceleration due to gravity in the vertical direction equal to negative 9.81 meters per second. And we know the initial velocity in the y direction is equal to 0, and that's stated in the problem that there is no vertical velocity. And finally, what we're searching for is this velocity in the x direction. This is our unknown. A good place to start is in analyzing this problem would be to look at our equations, our linear equations of motion in the vertical direction, because we seem to have a pretty good understanding of what's happening in the vertical direction. We know that the change in displacement, or the vertical displacement of the dog, is equal to the initial velocity in the y direction times time plus 1/2 times the acceleration times time squared. So this is our basic equation that we use to describe position and velocity and acceleration in the vertical direction. We know what the displacement is. We know what the initial vertical velocity is. We know what the acceleration is, and now we can solve for time. And by solving for the time, we can then back calculate what the horizontal velocity is. So what we can do is we can reorganize this equation, and we see that the time is equal to the square root of the change in vertical displacement divided by 1/2 times the acceleration. And when we put in those known values, which we can do, we see that this is negative 1 divided by 1/2 times negative 9.81. And this is in meters per second. And then we're taking the square root of that. We find that the time is equal to 0.45 seconds. In the next step, we'll use our equation for the horizontal displacement. So this is delta Rx is equal to the initial velocity in the x direction times time. And here in the x direction there's no acceleration component because we're ignoring any possible effects of air resistance. And now that we have this written, we see that we know the horizontal displacement. We know the amount of time that the dog is traveling in the air, which is governed by how quickly it falls and makes contact with the water. And so we can solve for this acceleration in the x direction. When we do, we see that the velocity in the x direction initially is equal to 8 meters divided by 0.45 seconds to give us 17 17.78 meters per second. So this is our answer to the problem number 4. And now what we can do is we can go ahead and continue solving, or we can go ahead and write and solve number 5. This is problem number 5, which is an extension of problem number 4. So we'll continue and solve that now. Problem number 5 is asking for the resultant velocity when the dog comes in contact with the water. So when the dog does a belly flop into the water, what is its resultant velocity? As a reminder, the resultant velocity is equal to the horizontal velocity squared plus the vertical velocity squared, and the F denotes final, so the final velocity in x, final velocity in y, and that quantity raised to the power of 1/2. So that's what we're trying to solve for. We know from problem number 4, actually, what we just solved for, that the velocity in the x direction at impact is equal to 17.78 meters per second. And so now what we need to do is we need to solve for the velocity in the y direction at impact, which is the unknown quantity. To do that, we'll use the equation where the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration times time. What this equation means is that when we think about the dog traveling through the air in the vertical direction, its vertical velocity at impact is going to equal the initial velocity that it has in the y direction, which is 0, plus the acceleration due to gravity times the amount of time that it's in the air, so that's the amount of that the dog will be accelerated to a new velocity. Let's go ahead and put in our known quantities. So the final velocity in the y direction is going to equal 0, so there's no vertical velocity initially, plus negative 9.81 meters per second squared, that's an acceleration, multiplied by the elapsed time, which is 0.45 seconds, that's a 0. And when we multiply that out, we see that the final velocity in the y direction is equal to negative 4.41 meters per second. So the units make sense, and the direction makes sense. This is a downward velocity, so that's consistent with how we defined our origin. So now we know the final velocity in the x direction and the y direction. We can solve for the resultant velocity. That's going to equal 17.78 squared plus negative 4.41 squared, all of that quantity raised to the 1/2. We find that the resultant velocity is equal to 18.32 meters per second, kind of squished on space there, but that's our answer to problem number 5.